Welcome to Module 5, Lesson 22, using sample data to compare the means of two or more populations. Okay, so in previous lessons, we've been challenged to learn some very important things, such as the roles that random sampling and sampling variability play in estimating a population mean. Okay, so this lesson here, 22, should be a quick one. It sets the groundwork for lesson 23, where you guys are going to be asked to informally decide if two population means differ from each other using data from a random sample taken from each population. So now you'll be looking at two different populations and seeing how close they resemble each other. Okay. Of course, we know that there will be sampling variability. All right. But we also want to calculate the means and then process the comparing of those two populations. They're going to be actually introducing something in this lesson, something that I've never heard of before, and I talked about something called standard deviation in the past, but in this lesson they're calling this mean absolute deviation. Deviation. Okay. So again, like I had mentioned, standard deviation, they're going to call this MAD, M-A-D, okay? And you can imagine absolute, of course, refers to, positive or negative, okay? So we're just talking about a distance away from the mean. So we are, again, I think pretty sure in the future, standard deviation is what you will be, we do look at it in terms of statistics, the standard deviation. They are going to introduce this mean absolute deviation. And if you don't know what deviation means, of course, that means kind of a distance, from a norm or whatever. And in this case, distance from the mean. Okay. If you deviate, that means you go off on a different path, different direction. Okay? So, in previous lessons, you worked with one population, and many statistical questions involve comparing two populations. Okay, which is truth. Just helped my wife with a statistics class, and very often we are posed with comparing two or more populations, actually. Okay, but for example, here are some that might be asked. On average, do boys and girls differ on quantitative reasoning? Oh boy, that's pretty heady. Do students learn basic arithmetic skills better with or without calculators? Which of the two medications is more effective in treating migraine headaches? Does one type of car get better mileage per gallon of gasoline than another type? Does one type of fabric decay in landfills faster than another type? And do people with diabetes heal more slowly than people who do not have diabetes? These are all very, very good questions, and boy, I'm sure have been the subject of some study at some point or another. Well, in this lesson, you will begin to explore how big a difference there needs to be in sample means in order for the difference to be considered meaningful. Okay? So you're always going to have variability. We know that baked into any type of statistical study, variability, which I've spelled wrong here, okay, I missed an L and an I. Variability is baked in, okay? It is something that we are to expect. But we will find out here, or we'll start talking about just how big a difference there needs to be in sample means in order for the difference to be considered meaningful. And if it is meaningful, if the difference is meaningful, then we can make some inferences or draw some quote-unquote conclusions, okay? Now the next lesson will extend that understanding to making informal inferences about population differences, and that's what we'll do in lesson 23, which is the last lesson in this module 5. Okay, so here's examples 1 to 3. Starting off here. Now Tamika's mathematics project is to see whether boys or girls are faster in solving Ken-Ken type puzzles. Okay, she creates a puzzle and records the following times that it took to solve the puzzle in seconds for a random sample of 10 boys from her school and a random sample of 11 girls from her school. Okay, so here we go. So she has here is her data that she has compiled here. Here is her mean for each one. Okay, and here are the boys. 10 of them, 11 girls. Here you can see the 10 boys here and the 11 girls here. Now again, the fact that there is one more girl, maybe not significant now, because we are looking at mean scores, mean time. Okay, and this is seconds here, so the mean time or the average time it took boys to solve this puzzle was 35.3 seconds, and girls it was 39.4 seconds. Okay, now the MAD or the mean, what's it called again? The mean absolute deviation. Yes. And then she has put the mean absolute deviation right here, which I guess we will be talking about right now. Okay. Down here it says, on the same scale, draw dot plots for the boys' data and the girls' data. Comment on the amount of overlap between the two dot plots. How are the dot plots the same and how are they different? So let's go ahead and take a look at that. So if you went ahead and made some dot plots for the data, it might look something like this here. Okay, we have boys on top, the top dot plot, and girls on the bottom, and in such a way we could actually take and we can compare them. And they don't look all that incredibly different. I mean, we know that the boys had a faster mean time, girls had a slightly higher mean time. Now these MADs, or these mean absolute deviations, gosh, I can't remember this, okay? Mean absolute deviations, they're not giving any kind of formula for these yet, because I know, again, this, let me just write this down here, mean absolute, and I'm going to keep forgetting this, absolute deviation. Again, like standard deviation that I had talked to you about before. I mean, the formula is kind of convoluted and kind of complicated. So I'm thinking they're just giving you these MADs here, these mean absolute deviations, just for comparison's sake. I don't think they want you to mess with that calculation. So when I give you those figures here, those numbers, and the importance here is that they're not different. And what they are measuring is how different all of these are from the mean. Okay, so you're getting an average difference that all of these, in the case of the girls, these 11 have from this. Okay, and that's what you're coming up with. With the boys, same thing. It's say you're trying to find out, you know, the average difference of all of these have compared to that mean. Okay, and just as a general rule, the higher this number, the worse. So you're looking for this number to be as small as possible. Okay, as small as possible, because you want you want all of the values as close as possible to the mean. Okay, you know, if that were that mean average deviation was 0, that means all of these numbers would be the same. Let's say the girls was, all of these numbers would be 39.4, okay, throughout. That's the only way you could get that. And that's really not possible, truly. Or very highly unlikely, okay? So you want this mean average deviation to be as small as possible, which means that your data is, the smaller it gets, the more clumped it's going to get. So if we look at these two dot plots up here, and we compare them, you can see the girls is rather symmetrical, ranges from, what's that, I think that's 32 to 47. Okay, it's quite a bit of symmetry here, like 1, 2, 3, 4, 5. There are 5, 5 on this side, and then the other 6 are on that side of the 40, 41. The boys maybe a little bit more skewed over here. 1, 2, 3, 4, 5. You got 6 over here. Then you got 4 on that side. And again, their range. Now these two boys here, who had these scores, looks like 27. They pretty much did. They pretty much account for this difference in mean. Truly, otherwise there's a tremendous amount of overlap because all of these scores here overlap. Okay. And I guess what I just did was I just talked about number 2, which was this one here. Compare the variability in the two sets of data using the MAD, the mean absolute deviation. Is the variability in each sample about the same? Interpret the MAD in context of the problem, and it is about the same. Okay, that variability is about the same. 4.04 and 3.96 are pretty close. Okay, close enough to say they're really not different. Okay, so I'm here on number 3 here. In the previous lesson, okay, that's lesson 21, you learned that a difference between two sample means is considered to be meaningful, okay, right here, meaningful, if the difference is more than what you would expect to see just based on sampling variability. So, you know, there's no true numerical definition there, but just it was meaningful if the difference is more than what you would expect to see just based on sampling variability. Okay, because things can be different based on sampling variability, but it gets to a point where if it's different enough, then you know that you are getting close to some real results. So the difference in the sample means of the boys' times and the girls' times is 4.1 seconds. Okay, so 4.1 seconds, and that's 39.4 seconds minus 35.3. Okay, and that's what we saw right here in our mean column. Okay, all right. This difference is approximately 1 mad. Okay, so now they're getting to this mad here. Okay, so this difference is approximately 1 mad, or 1 mean absolute deviation. Okay, so that's where they're getting one of those from. So, all right, let's just go from there, and we'll see if we can understand their use of this MAD. So if 4 seconds is used to approximate the values of 1 mad for both boys and girls, what is the interval of times that are within 1 mad of the sample mean for boys? Okay? So we're trying to get an interval, okay, that is within 1 mad of the sample mean for boys. So why don't you ponder that question? It's might seem a little bit obscure right now, and you might be like, huh? And if that's the case, that's fine, but I'd like you to pause just so you can just let that soak in, and just know that you need to apply this mad here, which we're saying 4.1 seconds is 1 mad, all right? And we know the mean times of the boys and girls, they're here and here, okay? And yeah, see what you can do with that, and then come back and we'll talk about it. Okay, so if you pondered and didn't figure it out, that is fine. Again, this is a new concept, and it's kind of just being thrown out at you here. And because we won't be doing any more statistics after these next two lessons, we'll be getting into geometry to finish the year. So maybe just something to have in the back of your mind. Maybe that's what they're planning, and I'm sure you'll be seeing this sometime next year. So here we go. So the way you figure this out, you're trying to find an interval. Okay, an interval is between what and what. Okay, so this idea they're trying to find you're trying to find an interval. Okay, what is the interval of times? So here's how you do it. So you take the mean of the boys, which is this number here, 35.3. Okay, that was the mean. All right, and I have it here and here. All right, and first you're going to take the MAD. Now they used 4 seconds here as the MAD. Okay, even though we figured it was 4.1 seconds here. Okay, so if you used 4.1 seconds, that's fine. I just used the 4 seconds that they recommended. I don't know, just getting rid of a decimal point, I guess, make it easier for us. So as it is absolute, so mean absolute deviation, okay, we are going to add 4 to get one end of our interval, and then we are going to subtract 4 from the mean to get the other end of our interval. So what this is saying, so if we have 35.3 is our mean, it's here in the middle, from 31.3 to 35.3, that is 1 MAD, okay, or mean absolute deviation. And then from 35.3 to 39.3, that is also 1 mean absolute deviation. Can you hear me almost forget those words again? All right, so between this place right here, between there and between there, they're both 1 MAD, okay? That is a mean average deviation. And again, this is something, well, the name is standard deviation in the parlance that I've heard it used. But yeah, so we use to compare your statistics, okay, to see how much, how close or how accurate your population sample is allowing you to get, okay? So that's what that means. And I know if that seems convoluted, you can just watch it again. You could watch other videos on it if you'd like. I mean, it's fun stuff if you're into this kind of statistics, numbers. I think it's a lot of fun. It gets a little hard to understand at times, but yeah, it can be fun. So that's what this is all about. So anyway, that was our interval. Our interval was between 31.3 and 39.3, and that's all you need to know. Okay, so anyway, here's B. B asks this: of the 10 sample means for boys, how many of them are within that interval? Okay, so how many fall between 31.3 and 39.3? Okay, let's go ahead and look. Look at our dot plot. Okay, and our dot plot will help us because we know that 31.3 is somewhere around here. Okay, and then 39.3 is before 40, so that's going to be right there. Okay, so we can see we have how many? We have 1, 2, 3, 4, 5, 6. We have 6. Whoops. 6. So 6 different scores were between 31.3 and 39.3. Okay, so 6 scores are within, we say, within 1 MAD of the mean. Okay, so 6 scores were within 1 MAD of the mean. Okay, so we look at the girls now. Let's look at the girls, the 11 samples. How many of them are within the interval you calculated in part A. In part A. Okay. Did I ask for girls too? Oh shoot. Okay, I'm sorry. I missed that. I was just doing boys. Why don't you go ahead and do girls? Find out the interval for girls now. Again, using the girls mean and the 4 seconds for the mad. Okay, and do so. Come up with something like this. All this here for the girls before we go on. All right, because I forgot that. Okay, so here's the here's the interval for girls. Okay, I went ahead and did the same as I did with boys, just using the girls mean. 39.4, adding 4, again plus 4, gave me 43.4, and then I took the mean again and subtracted 4 and got 35.4. So our interval is between 35.4 and 43.4. Okay, so if we go ahead and look at that, 35.4 and 43.4, we have, we start here, we have these two, 1, 2, 3, and it's like 4, 5, 6, looks like we have 7, so actually 7. We have 7 of the girls. Okay, so how many, this is the answer to C actually. It looks like we have 7 of those sample means for girls were within 1 MAD of the mean. Okay, so 6 for the boys, 7 for the girls. Okay, now the big question here, D. So based on the dot plots, do you think the difference between the two sample means is a meaningful difference? Okay, a meaningful difference. All right, that is, are you convinced that the mean time for all girls at the school, so this is at the school, not just the girls in the sample, is different from the mean time of all boys at the school? Okay, so this is a big, I mean, it's a huge inference, a huge leap to make here. Okay, first of all, always know that's a huge leap to make, especially when considering that there are only 10 in each of these samples. Okay, so if we look at these dot plots, I mean, there's a pretty huge variability here in the boys' scores, as you see, from low to high. Girls as well, quite a bit of variability. There's lots of overlap. Look at this, most of the boys and girls. Truly, when you look at that little section of it, okay, probably 8 of each, they'd pretty much be, they'd average out to be the same, okay, probably, or close to it anyway. So I would say, you may differ in your opinion, but I would say no, I'm not convinced because I think my sample size is too small, too much variability in this dot plot data, so we probably need a further study. Okay, well here's another example of a fun thing to do in class, which we won't be doing, but just imagine yourself doing it. You might want to do this with your with someone at home, though, just to collect some means. But 1 or 2 or 3 or 4 won't really be much fun or much to go by. But anyway, let's just go ahead and read this. So, how good are you at estimating a minute? You're going to work in pairs. So just imagine this: people are working in pairs. And what you're trying to do is, like, somebody puts their head down. Again, I don't want to read this verbatim because we're not actually doing it. But the idea, the data that I'm going to show you here, this is what these people did. So your partner would say start. Then you keep your head down and your hand raised. When you think a minute is up, put your hand down. I'm not sure why they didn't do it the other way, because that would be quite tiring to hold your hand up that long. Well, it depends how long a minute is, huh? But anyway, your partner will record how much time has passed, okay? And this first one here, what they've done is they've done this 2 different ways, okay? So what we're doing is we're comparing quiet So doing this while it is totally quiet, okay? And the next time you do it, the partner who is doing the timing is actually talking to the other partner who is deciding when the minute is up, okay? So there's a little bit of interference over here, okay? Interference, and whereas with the quiet, in the quiet there's not that interference, okay? So the idea here is we're comparing what the difference is there, okay? This estimation difference, all right? Okay, so what I did here then is I went ahead and got some data, okay, and here's that data, all right, and these are the times, and this is these are how many? 10, I think, 2, 4, 6, 8, 10, 12, 4. So 14 different people, okay, so a population or a sample size of 14 different people, all right, and those were the different times that had elapsed during these separate times, okay. You can see where it was quiet, okay, you get a good idea of how people did. It seems like they did pretty much better consistently when it was quiet, estimating a minute. So just imagine yourself and your head down and you're counting to 60 in your head, okay, and then you're going to put your hand down, all right. So I think I'd get pretty close, and as you can see, some of these people did get very, very close when it came to the quiet time, and even actually probably one of the closest here is one that came during the talking. That was right over here, 59.9 seconds. Okay, so they were darn close there. Okay, anyway, that's how the data was collected. All right. So number 4 asks us here to calculate the mean minute time for each group. Okay, so again, these are 14 different pairs of people, okay, who are doing these back and forth, and you're going to calculate the mean time for each group, all right? And then we're going to go ahead and find that difference between the quiet mean and the talking mean. Remember, we did that before in the last lesson as well. Okay, so if I go ahead and do that, all right, so the quiet mean was 58.8 seconds. The talking mean was 64.8 seconds. All right, so that you would, of course, add all those up. Okay, add all of these up, and then divide by 14. Okay, so and then talking, same thing. All right, so you'd go ahead and so there are mean. Okay, our means. All right, we have our means. Now the difference, okay, between those means is 6 seconds. Okay, now again, this is the difference between the means. Okay, between means. All right, which is very important. All right, very important. There's a difference between means. 6 seconds. Okay. All right, so 6 seconds there. Okay, so now what we're going to do is just go back here and read. So we're going to read down here first, number 5. So on the same scale, we're going to draw dot plots of the 2 data distributions. Okay, and that's this data distribution right here. Okay, we're going to draw those on 2 dot plots, one on top of the other, and we're going to go ahead and discuss the similarities and differences we see in those 2 distributions. Don't want to do that. Do want to do that. I'm going to just watch this these dot plots grow here. Okay, here is the is this the quiet one or the? Oh, actually, that's just the scale I've drawn. Okay, and when they say on the same scale, that's exactly what they mean. So this is our scale down here. So everything just transfers from top to bottom. So they're drawn on the same exact scale. Okay, because this makes it easier to compare. Okay, so if I go ahead and do this, then I can go ahead and populate this. Here, let's go ahead and do this first. We'll get our data. Get our data in front of us. Okay, and that's the quiet. Those are the quiet scores. Okay, and here are the talking scores. Okay, so we'll go ahead and transfer that data to the dot plots, and there you just see it. Okay, and you can see the difference here, difference and similarities. It looks like you could look there. That has there's quite a bit of overlap as you can see right in this area here. Quite a bit of overlap all over here. Okay, some overlap between the two dot plots. All right, the quiet distribution is fairly symmetric. Okay, this is quiet up top here. This is quiet, and this is the talking. All right, so it's fairly symmetric. You can see here's our range right there between, what was that, 54 point some odd, and then 64 point some odd. I mean, this is pretty symmetric. Put a line down the middle there, and pretty darn close to being symmetric. Whereas the talking one, a little bit more varied. We'll see a little more variance in that one there. Okay, a little more variability. Okay, actually, what else can we say about this? Okay, so yeah, and you can see where the centers are, probably about, see here, you can see this one's probably about 60 or so, and here probably somewhere around there, around 65 some odd seconds. Okay, all right, so let's go ahead and move, whoopsie daisy. Yeah, okay. All right, so we're going to go ahead and do a few things now. We're going to go ahead and calculate the mean absolute deviation for each data set. Okay, so, and then based on those MADs, okay, MADs, we're going to compare the variability in each sample. Okay, questions we're going to ask ourselves are, is the variability about the same? And then we're going to interpret the MADs, the MADs, in the context of the problem. Okay, so let's go ahead and get the data up in front of us. All right, let's let this go a little faster. Here we go. All right, and again, these are the quiet and talking scores, as you can see right there. Okay, these were the quiet scores here. These are the talking scores here. Okay, so what we're going to do first is we're going to go ahead and calculate the mean absolute deviation, all right, for the quiet group right here. We're going to work on this one. I'm going to show you how to do this right now. Though nowhere in my notes here does it talk about doing this, but I want to show you how this is actually done, which is actually pretty neat. Okay, so the first thing we need to take into consideration is that we have this quiet mean of 58.8 seconds, and what we want to do is we want to compare that 58.8 seconds to all of the actual times. Okay, this is just the mean of all those times. Okay, the average of all those times. We want to compare this with all of those, and then come up with this mean absolute deviation. Let's go ahead and watch that. Let me get rid of some of this. Watch that happen. So here we go. Okay, so what I'm writing up here, okay, are the differences. Let me just stop for a second and explain, because I didn't want that to go so fast. Actually, I'll go back to my slower speed. So right here, for example, this 0.7 here, that is the difference between 58.1 and 58.8. Okay, and then I go ahead and find out the difference between 56.9 and 58.8. So I'm always using the mean in comparison, and then I put the difference here. That's the difference between those two. 60.1 and 58.8, 1.3. Okay, so you can see what I do. I'm going as I go along. All of these are the differences between the individual scores or the individual times and the mean of all of those times, or the average of all of those times. Hopefully that makes sense to you. I'll just continue populating this, and there you go. So those are all of the differences, okay, differences between the actual time recorded and the mean of all of those times, all 14, and that 14 is a very important thing to know, because we need to know what we are going to divide this by. So the idea now is to add up all of these. Okay, if I add up all of those, and then I divide by, of course, 14, okay, so there are 14 of them, I will come up with an MAD, a mean absolute deviation of 2.68 seconds. Okay, and what that means is that the average difference of all of my individual scores and the mean of all those scores is going to be 2.68 seconds. And again, this MAD and also this MAD and also the standard deviation I've been talking to you about are all ways of testing the accuracy of the data, the viability of the data, reliability of the data, etc. Okay? All right, so that is for the quiet times, okay, the quiet measurements or estimates. All right, let's go ahead and erase all that. And actually, I need to erase. I think I added some stuff. Oh, wait, hold on. I didn't want to do that. Oh, yeah, I did. That's fine. Okay, so let's go ahead and write that up here. The quiet MAD, quiet mean absolute deviation, is 2.68 seconds, just to keep that as a reference. All right, so now we're going to go ahead and work these out. Now, if you want to, or I'd like you to, just pause, go ahead and figure out the mean mean absolute deviation of those. Okay, and just one piece of information you would need is that the talking mean equals 64.8 seconds. So if you use that, 68.8 seconds, and all of those individuals, you will do what I just did prior to this. So go ahead and do that. Come on back and let's see how close you get. Okay, I did that again, where I started talking, and I'm not sure if you heard any of what I just said. So I'm so sorry. Must be a little tired here. So anyway, what we're going to do here is we're going to go ahead and use our calculations to find out if our time estimates are the difference in the time, the mean time estimates is meaningful. Okay, because we had a difference of 6 seconds. Okay, so we're going to look. Let's look back. No, let's do this. Let's go ahead and look back here. Okay, we know that there was a difference between means of 6 seconds. Now, that would mean that quiet estimation, okay, is much more efficient or much better than talking estimation. Okay, because quiet the mean was 58.8 seconds, which is only 1.2 seconds away from a minute, whereas talking mean was a whole 4.8 seconds away. All right, so this 6 seconds here is a difference in the means, which is saying that it's saying that that is the difference between those two. So we are going to check now whether that 6 seconds difference is meaningful enough to allow us to say, yeah, quiet estimation is better or more efficient. Okay, let's go ahead and test that. This is how we test that, is with these MADs. All right, these mean absolute deviations. Okay, and again, I've got to get through all of this first. Okay. All right. So again, we have, not again, just first here. So we have the difference in the means is 6 seconds. Now, we are trying to find out how many MADs separate the two means. How many 2.73 seconds there are between the two means. All right. So we're going to take that 6 seconds, which is the difference in the two means. And then we're going to go ahead and divide it by 1 MAD. Okay, and that makes sense. And in this case, we're going to take the bigger one because these two are so close. so close right here, 2.68 and 2.73, that they're just virtually the same. So we're going to choose the larger one because that's what they told us to do. All right, and then we go ahead and we do our division, and we get 2.2 mads separating the means. Okay, so there's 2.2 mean absolute deviations that come between the means. Now, on the surface, that doesn't help us because we need something as a benchmark or a baseline, and that baseline is 2. So when the number of mads is greater than 2, then it equals meaningful. Okay, so when those mads are greater, the mads that separate those two means, okay, that came between those two means, are more than 2, greater than 2, that means it is meaningful. All right, meaningful in the sense that we can say to ourselves, more or less safely say to ourselves, that the difference in those means over here is not just because of sampling variability, because sampling variability is always going to mess things up in some way, shape, or form. But after performing this measurement here, we can safely, quote unquote safely, say that that difference of 6 seconds between the quiet estimation and then the talking estimation, that difference is due to something other than sampling variability. Okay. Alrighty. So I hope that's clearer than mud. All right. And here we are at the lesson summary. And again, the last lesson in this module 23 will look further at this, so we can use these newfound skills and knowledge once again. All right. So here we are, lesson summary. Variability is a natural occurrence in data distributions. It just is. It's something you cannot get away from. We are humans. Much of what we do is a human endeavor in statistics. Therefore, you're always going to have some variability. People are different. Sampling is random, which sets us up for all kind of randomness in our data, which can make things not look consistent. Now, two data distributions can be compared, okay, by describing how far apart their sample means are. The amount of separation can be measured in terms of how many mads, okay, and again, mads, that's one more time, mean, so I can remember it, absolute deviations. And again, that idea of absolute just means that you just disregard the negative or the positive, okay, because it could be a negative or a positive number, and it's just that distance, okay, remember our absolute value idea, okay, how many mads or mean absolute deviations separate the two means of two data distributions, all right? Note that if the two sample mads differ, the larger of the two is used to make this calculation, okay, and that's what we did at the end there. So anyway, I know it's unfortunate this is probably the last. I mean, we'll do it in lesson 23, then you won't be doing it much at all thereafter this year, because this is a lot of fun. I feel like if you are getting this, you are just right at the beginning of really coming to understand all of this. Hopefully you will retain or keep some of this knowledge when you do move into statistics later on. Anyway, good luck on the problem sets, and see you next lesson.